So real numbers is the topic for the session. So what are real numbers? And what are the different types of numbers which we already discussed in the lower classes, where we have studied each of different types of numbers like natural numbers, integers, and rational numbers, irrational numbers, etc. and etc. So these are all the numbers which we are going to discuss in today's session. So before we start with real numbers, let's start with a mapping diagram on what the different kinds of numbers are. Say for example, we know that we have natural numbers denoted by n, then we have whole numbers denoted by w, then we have set of integers denoted by z, and we have set of rational numbers denoted by q, and then we have finally the real numbers denoted by the symbol r, a Roman r. So these are the different types of numbers which we are going to discuss in today's session, mostly about the real numbers. Now coming to the natural numbers, we know that natural numbers obviously start with 1. The least of the natural number is 1 and the highest is undefined. It can be any big value, but initially it starts with 1. I have natural numbers as 1, 2, 3, 4 and so on and so forth till infinity. Similarly, when I start with whole numbers, the only difference out here is that it has an additional 0 along with the rest of all the natural numbers. So if 0 is included with the natural numbers, I get whole numbers in the form of 0, 1, 2, 3 and so on and so forth, this being the additional element. Next, I have the integers which start from negative infinity and accepting all the negative numbers in the form -3, -2, -1, 0, 1, 2 and 3 and so on and so forth. So these are the types of numbers which are called integers. Integers have both negative and positive numbers, including 0, which is neither positive nor negative. Then I have rational numbers, which is defined in the general form as p over q, all the numbers in the form p over q, such that it satisfies with two conditions. One is that p and q must be integers, and secondly, the condition is that q should not be equal to 0. So under these two conditions, all the numbers in the form p by q are called rational numbers. We're going to discuss about rational numbers more briefly out in case of this topic, but before that, let me also define the real numbers, which are given in the form of p by q such that q is not equal to 0. So what is the difference between rational numbers and real numbers? Rational numbers has the restriction that both the p and q, which are considered in the numerator and denominator respectively, must be integers, but in this case p and q need not be integers. It can also be any number which is not an integer too. But in both the cases, the rule is that q should not be equal to 0, because any number where the denominator is 0 is said to be an undefined value, and hence the restriction for both the set of number system is that q is not equal to 0, and this is how I define each of the sets of numbers in the real number system. Now to come more briefly with q, we call q as rational numbers. So what are rational numbers? More briefly, as defined here as p by q, such that pq belong to z and q not equal to 0. Let's take with some examples as a recap of already discussed topic in the previous sessions in the lower classes. So let's take some examples for rational numbers and see what type of numbers are rational numbers and what type of numbers are not rational numbers, as a recap from the already learned topics of the previous sessions. So for example, I take 4 over 5, then this is clearly a rational number because p and q, where p is 4 and q is 5, accepts the condition that p and q are integers, and q being 5 is not equal to 0 because 5 is clearly a non-zero number. Therefore, I can say that this is a rational number based on condition 1 and condition 2, under these two conditions of q. Similarly, let me take another example. Say I had taken 7 over 0. So in this case, this is not a rational number because 7 and 0 are integers, but q should not be equal to 0. But in this case, with this condition is failed. In case of the example, it's 2, 7 over 0. Similarly, if I take another example, say root 6 or root 5, then root 5 is not a rational number, because if you take this in the form p by q, where root 5 can be written as root 5 over 1, then root 5 is not an integer. So p is not an integer. Therefore, this fails the condition of being a rational number. Similarly, if I take more further examples, say for example, I take root 4 by root 9. I wanted to test for this being a rational or an irrational number. So in case of this, I simplify further to identify whether this can be simplified more further. So let's see if we can simplify this. So we know that square root of 4 is 2. And we also know that root of 9 is 3. So that the simplified answer for root 4 over root 9 is 2 over 3. Thus, this satisfies both the conditions of a rational number, with 2 and 3 being integers and 3 not equal to 0. Is how I identify the two cases, and hence proudly I can say that root 4 over root 9 when simplified is a rational number. But the same problem, if I just take it in the form root 4 over root 3, then this is not a rational number, because though I can simplify this to be root 4, which is 2, and this can be written as root 2 over root 3, because root 3 cannot be further simplified. Therefore, 2 over root 3 is the simplified part of this, but cannot be further simplified. This fails the condition of rational numbers, because my first case says that p and q must be integers, but p is an integer, but q is not an integer, because q is root 3. A root 3 cannot be an integer, and therefore this fails the condition of being a rational number. Now, to understand more further on what are rational numbers, we have already discussed about the terminating and non-terminating, recurring and non-recurring decimals. So let's come back to the revision of as a recap for terminating and recurring and non-recurring decimals. So when I take the example of 3 over 2, then I call this as a rational number because p and q are integers and q is not equal to 0. Then the reason being that this can be simplified to a limited decimal value. So when I simplify this, I get this as 1.5, which is a simplified decimal. I have the minimum decimals for this. But the same problem, if I just take it, say if I take root 2, then my root 2 is not a rational number. Why? Because its decimals are non-terminating and go on repeat, repeat and repeat. So for example, if I take the form root 2, I can write this as 1.4142135, so on and so forth. The square root of 2 is approximately this, and it never ends. The values repeat and repeat. So these kind of problems which do not give the which are not expressed as perfect decimals are called irrational numbers. They are not rational. They are opposite of rational, which are irrational numbers. Therefore, this cannot be a rational number, but this can be a rational number. If you understand this in the decimal concept, this is how we understand the rational numbers and the one which is not a rational number. Next, coming to the example of pi. Now, pi is called an exceptional irrational number. This cannot be rational because this is one mysterious, most famous value in mathematics, which is still a mystery, is identified to be the most powerful number, pi. We all know about pi. So circumference by diameter is pi. So in this case, pi is also identified as a rational number because it keeps on, it's called an exceptional irrational number because it keeps on repeating and repeating, but it does not give a fixed value. The most approximate value of pi when expressed in fractional form is 22 over 7, but not exactly equal. Mathematicians are still finding out the methods to find the exact value of pi. Pi is not exactly 22 by 7, but approximately this, which on approximation gives 3.14 dash dash dash, a never-ending value of pi. So similarly, this is how we identify the rational numbers in mathematical number system. Now, let's see how each of the number system like n, w, z, q and r are related to each other when you understand that in the Venn diagrammatic notation. So when I take the Venn diagrammatic notation between the relation between n, w, z, q and r, there is a very good relation between each of the numbers which we have discussed in the previous sessions. Natural numbers, whole numbers, integers, rationals and real numbers are very much associated by taking them in the form that if I have my first set of numbers are said to be the natural numbers. Next, my second set of numbers, which are whole numbers, is said to be the superset of n, because all the natural numbers are there in whole numbers, but all the whole numbers are not there in natural numbers, because 0 is one additional value in w which is not present in n. So n is said to be subset of w, or w is said to be superset of n. In diagrammatic form, we identify in this form, n inside w. So n inside w is what we understand in subset notation. Next, I have w inside z because all whole numbers are present in integers, but all integers are not present in whole numbers, as we can clearly see with the set of different numbers. So I have this where z consists of w in turn n. So both n and w are inside z is how I understand this diagrammatic notation. Similarly, n, w, z are all there inside q. So n, w, z are all subsets of q or part of q, and q is the superset of each of n, z and w is how I understand this. Then finally, the superpower, real numbers. So the most powerful person out here is the real numbers. He is the Superman. When you compare each of n, w, z, q and r controls each of the numbers because all these numbers are present in R, and hence it is called set of real numbers consisting of each of the numbers which we discuss out here in this case. So this is the diagrammatic notation of understanding the numbers in Venn diagrammatic symbols n, w, z, q, r, and this leads to make me understand n is subset of w subset of q of z subset of q subset of r is how I understand in the subset notation, and this diagram is how I understand the presence of one set in the other set. Now comes the concept of irrational numbers. Now irrational numbers are the numbers which are not rational. So therefore between R and Q I have some region which is covered in the form of a ring. So this region includes, so this is the region which includes all set of irrational numbers which are denoted with R minus Q is irrational numbers denoted with R minus Q. All real numbers or rational numbers taken out of real numbers will be left over with irrational. So this region will give me, the shaded region gives me the set of irrational numbers and taken out in different cases. So let's take some exercise problems where I wanted to find the answer for this question. Is 2 by 5 a terminating, is 2 by 5 a terminating or a non-terminating number is my question. So in case of this problem, I'll try to identify whether this is a terminating or a non-terminating number by just simply dividing and identifying the number of decimals. So if I take this and divide this with 5, 2 divided by 5 gives me 0, 5 4s are 20. So remainder is 0, therefore 2 over 5 is 0.4. Therefore this is a non-terminating decimal because it doesn't terminate, it restricts itself in. It is a terminating decimal because it ends with some decimal, sorry. So in this case, when the decimal is ending with a finite value, it is terminating. So 2 by 5 is a terminating decimal, as can be seen here with an example. But when I take, say for example, 1 over 3, so I wanted to know whether this is a terminating or a non-terminating decimal, then immediately I just try to divide this 1 over 3, which gives me 0.339, 10339, etc. And therefore my 1 over 3 gets reduced to 0.3333, so on and so forth. So clearly I can identify that it doesn't terminate. So therefore I have this as an example of a non-terminating value. So 1 by 3 is a non-terminating value or a repeating decimal because 3 gets repeated all the time. Therefore 1 by 3 is a non-terminating or repeating decimal value, and then 2 by 5 is a terminating value, is how I understand between the terminating and non-terminating decimals. So now that we have discussed about the different types of numbers, we also know what are prime numbers and composite numbers. So what are prime numbers? Prime numbers are the numbers which do not have the factors. The only factors for prime numbers are 1 and itself. So for example, I take the number 3. Then I cannot have different factors for 3 except I can write this as 3 times of 1. So this is an example of a prime number. But say for example, when I take the number 6, this is not a prime number because the number 6 can be expressed as product of factors. Like you have 6 which can be expressed as 2 times of 3, but 7 which cannot be expressed except with 1 and itself. So the numbers which can be expressed as product of different numbers other than 1 and itself are said to be the composite numbers. And the numbers which cannot be expressed as the product of 2 different or more than 2 different numbers except 1 and itself are said to be the prime numbers. So in case of this, 7 which can be expressed as product of 1 and itself is strictly by the definition a prime number. But same case when I take with 6 which can be expressed as product of 2 different numbers which are not 1 and itself, then at least if you can identify one factor which can satisfy the product which doesn't consist of 1 and itself are said to be the composite numbers. So this is an example of a composite number, and this is an example of a prime number. So there are different cases through which we identify the composite and prime numbers. So what about 91? 91, is it an even or an odd number? Is how I had to check. 13 times 7 is 91. So definitely this should be a composite number. It cannot be a prime number because the factors of 91 are 13 and 7. So it is an example of a composite number. So with this discussion of prime and composite numbers, which we already discussed in the lower classes, now comes the most important theorem in mathematics connecting the prime and composite numbers, called the fundamental theorem of arithmetic. So let's see what's the definition or what's the statement which makes the theorem. So fundamental theorem of arithmetic states that any number any integer, because I start with integer, so any integer can be expressed as product of prime factors. So this is the theorem which has come after studying the prime and composite numbers. So let's complete the statements and discuss on how this statement supports for different numbers. So any integer can be expressed as product of prime factors, and the product is unique in whatever order the prime factors are considered. So this is how the fundamental theorem of arithmetic has been stated. So let's reconsider the case. It says that the definition of the statement of fundamental theorem of arithmetic says that any integer which we consider can be expressed as product of prime factors. That means any number you take in as which is an integer that can immediately be expressed as product of prime factors, any number. And the product is always unique. You cannot get two different factors for each of the cases. It would be different. Then in this case, the product is always unique in whatever order the prime factors are considered. So let's support this statement with different examples and see whether the statement is true or false. So to start with, let me start with an example. 24. As I know that 24 is clearly an integer, then I see that this can be expressed as different product of different factors. So let's try to find all the possible factors using the LCM method. So I have this 24, then starting with 2. Therefore, 24 can be written as 2 times of 2 times of 2 times of 3, which in turn gives me 2 cubed times of 3. So therefore, I can write 24 as 2 cubed times of 3, where each of the factor is identified to be a prime number. 2 and 3 are prime numbers. So my statement which says that any integer can be expressed as product of prime factors stands true. I have taken the integer 24, and when I express it as a product of factors, I get this to be all primes. Is a very important statement which has been derived from fundamental theorem of arithmetic. So similarly, the statement also extends itself, stating that the product is unique. Unique means one and only one. So this product cannot be changed. If whatever order the prime factors are considered, this cannot be changed into different forms. Now whatever factors I got here must be fixed and unique. This is the only one and only one possibility for expressing 24 as product of different factors. You cannot get any other form where that can also state that the product of those factors also give me 24. It is not possible. It is a very important research which has been made in prime and composite concepts. So therefore, the fundamental theorem of arithmetic finally makes us understand that you take any number which is an integer can be expressed as product of different prime factors, and the product is unique. To support with one more example. Let me take 54. So I have the number 54, which I can write it as so I can express this as 54, which can clearly be expressed as 3 times of 3 times of 3 multiplied with 2. So 54 multiplied with each of 2 and 3 clearly makes me understand that all of the numbers which are considered in the product are primes. 2 and 3 are primes. And the product is unique. You cannot change this into any other form to multiply and get 54 in whatever order the prime factors are considered. Therefore, these two examples finally conclude that any integer taken into consideration can be expressed as product of prime factors and the product is unique. So some mathematicians modify this term integer with a composite number because the product of factors is generally the very much connected definition of a composite number. Therefore, an integer here is more replaced with a composite number. Therefore, my statement can be reread as any composite number can be expressed as product of prime factors and the product is unique in whatever order the prime factors are considered. So 24 is a composite number which can be expressed as product of these 2 cubed times 3. 54 is a composite number which can be expressed as 2 times of 3 cubed. Is how I understand the concept. This can also be applied for a non-composite number. Say I take the prime number 13 is again expressed as 13 times of 1 expressed as product of primes, 1 and itself. So more modified statement replaces integer with composite number. The Lcm and Hcf are two different important factors of mathematics while solving many of the problems, and we have discussed about Lcm and Hcf in the lower classes. So let's come as a recap to discuss about what is Lcm and Hcf in mathematics. So Lcm, which stands for least common multiple, and Hcf, which stands for highest common factor, are the two important aspects we are going to discuss today with examples. So here, if I take two numbers, let me start with Lcm and Hcf, the least common multiple and the highest common factor. So if I take two values, 12 and 18 are the two numbers I take, and I want to find the LCM of 12 and 18, and I want to find HCF of 12 and 18. So let's see how we are going to find for each of the answers and then differentiate between understanding the LCM and the HCF. So coming to this, let me start with 12, and using the prime factorization method, I should be able to find all the possible products in primes for 12. So as we know that 12, when taken in with prime factorization method, 2 times of 6, 2 times of 3 can be written as 2 square into 3 power 1, because 4 3s are 12 and there are two primes which are 2 and then 3, which can be written as 2 square times of 3. Therefore 12 can be written as 2 square times of 3 power 1, because these are the possible factors in prime, the prime factors for 12. Similarly, I find the prime factors for the other number in this example being 18. So when I want to find the product of primes for 18, again I try to find by prime factorization method the different possible factors, 2 9s, 3 3s and 3 1s, so that 18 can be written as 2 power 1 times 3 square, as can be seen from here. 2 into 3 into 3 can be written as 2 power 1 times 3 square. Now with these two, my LCM, if I wanted to find the LCM of 12 and 18, then I use the method where it says that LCM of 12 and 18 is nothing but the product of the greatest powers with common prime factors. Now LCM of two numbers is defined as the product of the greatest powers with common prime factors. This is how we understand LCM connected with prime factors. So let's see how we can simplify the LCM of 12 and 18 using this exclusive method of identifying the product, identifying the greatest powers with common prime factors and then multiplying them. So in this case of 12 and 18, I identify that the greatest power here is 2 power 2 and the greatest power here is 3 power 2. Therefore, for each of them, the product of the greatest powers with common prime factors. So here I find the common prime factors 2 squared and 3 squared. Therefore, the greatest powers here are this and this, which I'm going to multiply as 2 squared times 3 squared as the product using the statement out here. So in this case, I get this to be 2 squared, which is 4, and 3 squared, which is 9. 4 times 9 is 36. Therefore, LCM of 12 and 18 is said to be 36. So LCM of 12 and 18 is 36 by using this concept. The least common multiple of 12 and 18 is equal to 36. So coming to the next, if I wanted to find the HCF of 12 and 18, the highest common factor of 12 and 18, then also I have a formula similar to this LCM of two numbers. So when I wanted to find the HCF of 12 and 18, then this is identified as the product of the least powers, here being the greatest powers. I have here product of the least powers with common factors, with common prime factors. So when I identify the least powers here, clearly I identify that the least power here in case of 12 is 3 power 1 and the least power here is 2 power 1. Therefore, when I want to find the HCF of 12 and 18, I take the product of the least power 3 power 1 times the least power in case of 18 2 power 1, so that I get this times this, and this gives me the answer to be 3 times of 2, which is 6. Therefore, the highest common factor of 12 and 18 is 6, and the least common multiple of 12 and 18 is 36. Is how I identify the difference between understanding of LCM and HCF. So similarly, there's a small note I would like to make here, that HCF is also called is sometimes referred as GCD, the greatest common divisor. The highest common factor is also referred sometimes as greatest common divisor, abbreviated as GCD. Next, one of the most important relation between LCM and GDC in understanding through the connection between LCM and GDC is that they are very much related through a mathematical equation, where if I wanted to find LCM and GDC of two numbers, say A and B, my numbers are A and B, then LCM into HCF is the product of the numbers. If I wanted to find LCM or HCF, I can also use this formula if provided I know one of them, either LCM or HCF, but they are two connected with LCM times HCF is equal to A times B. the LCM into HCF is product of the numbers is how we understand the concept in this relation. And this is very important because this connects HCF and LCM with a mathematical equation.